So welcome. We're going to do moment of inertia. And moment of inertia is rotational mass. And the equation, I just bring the equation out. The equation is basically, it's, you imagine this object, whatever it is. We imagine the object being made up by a whole bunch of little cubes of stuff. And we pick a rotating axis. We've got to pick the axis. I'm going to say the axis doesn't have to be symmetrical, although they are the easier ones. But I'm going to say let's rotate it about that axis. So imagine it's a bowling ball, and there's my axis of rotation. For each one of those little masses, I have to say how far am I away and what is the mass inside. And I do this calculation. I say my moment of inertia is equal to the sum for each mass of the distance from the turning axis to that mass squared times the mass. So I see if I take the same mass and move it twice as far away, it's not twice the effect, it's 4 times the effect. If I take the same little mass cube and move it 3 times further away, it's not 3 times the effect, it's 9 times the effect. So very quickly, masses that are big distances from turning axes really slow down the acceleration. And you kind of know this to some extent. When you're, let's say when you were a kid and you're going, everybody walked on top of a wall. There was a wall on the edge of something and they all climbed the wall and then walked on top of it. When you start to feel uncomfortable, what's the first thing you do?
Lower yourself.
Pardon?
Lower yourself.
You crouch.
Right.
Yes, so I'm walking, and I crouch, and what else do I do? Put my arms out. What am I doing? Why am I putting my arms out? I'm moving this mass further away from the turning axis. I'm increasing my moment of inertia, which is increasing my rotational stability. Do you want to make it really easy? Get yourself a big pole. Carry the pole. When you start feeling uncomfortable, lift the pole up. You see that all the time if you go to Cirque du Soleil or a circus. You don't see circuses anymore. But you see tightrope walkers doing that. And what they're doing is they're using this pole. It's kind of amazing. I used to think, oh man, and he carries a pole as well, you know. Not only can he walk on a tightrope, but he can carry a pole as well. And it's like, no, he's carrying a pole so he can walk on a tightrope, you know. So that distance, just a small change in the distance, makes a big change. So moment of inertia is the angular equivalent of mass, and here's the equation for it. And what we need to do now, and so let me just mention this. If I have a object like a pen, for example, I can have one moment of inertia about that axis. That will be I1. I can have a completely different moment of inertia about that axis, I2. And I can have a different moment of inertia about that axis, I3. And of those, I2 is the smallest because all the mass is relatively close to the turning axis. And I1 is the next because this distant mass is not as far away as it could be. And I3 is the biggest because that mass is long, long way away. So your moment of inertia is not about the object. It's about the axis through the object. It's kind of slightly different, so watch out for that. There's a couple of examples of different ways we can do it, and the first example is we're going to do it. This is a little project here. I hate using the diagrams that are given to me, but this is a pretty good diagram actually. And then this is going to be so those are my masses.
I got a 3 kilogram, a 5 kilogram, a 4 kilogram, and I got a turning axis. And then rest is I just need to work out. So I say that my moment of inertia about that turning axis is equal to the sum of each separation squared times my little bit of mass, and that's it. Yes. Now, why was I hesitating there? Because recently we did some work where we said, what was it? We said that our center of mass is equal to the sum of R M over the sum of the M. Or I said X. Remember that? Yeah? Remember that? We just did it a couple of sections ago. Can you see how it's just similar enough that it's going to trip you up if you're not careful? So again, you've got to separate these two. Don't just get those two equations backwards. So watch out for that. It's if you set a little alarm bell and say, I better not put down the equation for the center of mass, because this is different. Then I just go around and say, well, I naught is going to equal, just pick one. So let's do the easy ones first. So we'll do that's 2 meters there. So that's going to be 2 squared times 5. Then let's add on to that. Let's do the one down here. It doesn't matter about it being in a negative direction. It's going to be 3 squared. If you want to put down minus 3 squared, it doesn't matter because minus 3 squared is the same as plus 3 squared. And that's going to be times 4. This is the one that's a little bit not so obvious. I do want that distance.
Where'd you get the 2?
I got the 2 from here. Yeah. Yeah, cool. And then, so this is going to be this is 3. That's 4. What's this? 3, 4, 5. So if you're kind of cunning, you can just spot it's 5. If not, you would say r squared equals a squared plus b squared. So r squared equals 3 squared plus 4 squared. So r squared equals 25, so r is equal to 5. So you can work it out, but often teachers like to be kind of kind and they go 3, 4, 5. I'm going to use a right triangle, do I not use 3, 4, 5? And then they don't need to do that bit of math. But if you don't spot it, you've got to do the math. You know? So that then gives me 20, 36, 75. So I naught is equal to 75 plus 36 plus 20. I naught is equal to 75, 95, 131. 131. The units are going to be, just look at your equation. It's going to be meters squared, and there's going to be kilograms in there. So let's just say kilogram meter squared. If you put down meter squared kilogram, it will be just acceptable, just as acceptable. But most people will say kilogram meter squared. So not bad. Just can't get confused about the equation. But let's go to a distribution of charge, a distribution of mass. I said charge because we do something very similar in physics too. If I have a potato and I put an axis through the potato, I can imagine dividing this up into a whole bunch of little cubes. And for each little cube, I'm going to say, how far are you away from the turning axis? You know, and just sum. You know, that's what I'm going to do. That would be I is equal to the sum of r squared m, delta m really. And then if I go to, well, let's do this let's take these finer and finer little delta m's. So that goes to the integral of r squared dm. And I don't know about you in calculus. I was kind of like, I was introduced to calculus in a really weird way. I had a teacher who just like introduced bits to me before I did it like formally. And I remember he was kind of making out like that curly told you were doing an integral, and so did the dm. It was like the front and back of a train. And so I got the idea that the dm had no physical meaning. It was just a symbol that was part of the symbol, like you have in music, you have the treble clef and all that. But the dm does mean something. It's the little bit of mass. It's the little bit of mass of the smidgen of a cube that you have. So I got completely the wrong idea when I began my calculus, thinking the dm or the dx or whatever was just a symbol that says, oh, you're going to do an integration. You're going to do an integration, but or a differentiation or whatever, whichever form it was in. And I was completely confused for a while, actually. So let's do some of these. Now, what do we do in physics to make life easier for ourselves? It's not a calculus class, so I don't want you to, I'm not going to try and make the calculus as hard as possible. I'm going to try and make the physics the focus. So I have these set pieces that we've seen before. I say using the method as shown in physics class. This is what I want. So this is a classic one. And we're only going to deal with one shape for this. But it's an important shape, and that is the flywheel shape, or we call it the solid cylinder. So here's my solid cylinder. And the axis I'm interested in is going through the middle of it. What we call the symmetrical axis. It's the only axis that's symmetrical. I say using the method of calculus as shown in physics class, show that the moment of inertia of a solid cylinder about the axis through its circular center is a half mr squared. I wouldn't ask you exactly that. I'd say, what is the moment of inertia? Show. I wouldn't say show. I'd say, what is it? But you've got to use the method as shown in physics class. Okay. So I'm going to rather than a slice, I'm going to take a sleeve of stuff. I need to just go back and do just a little bit more in purple. So this is R, and this is T. I'm going to call that one there is going to be little r, and that there is going to be called dr, and that mass is going to be dm, is mass of sleeve. Yeah, and I'm going to say big M is mass of solid cylinder. And my principle is that my moment of inertia is equal to the integral of r squared dm. Yeah, I have no idea how to do that because I don't know how to integrate r squared with respect to dm. So I need to do a little bit of a sidestep. Convert dm into something dr. And so what I say is dm is equal to, now we could do this as an area because it is symmetrically deep, or we could do this as a volume, and I tend to do them as volumes. There's no reason why I should. I could do it as an area, but I'm going to say it's the dm is equal to the volume sleeve times the volume density. That is literally what dm is. So dm is equal to, and for the volume of the sleeve, I'm going to imagine taking that sleeve and unrolling it. And so I have a thickness here which is dr, and I have a height here which is t, and I have a length here. What would that length be in terms of little r? What would you call that length in words? It's something to do with a circle. What is that? Circumference. And so what would that expression be for the length of the circumference? 2 pi little r, yeah? 2 pi little r, not big R, 2 pi little r. I'm going to distinguish between those two. Okay. So then I say, well, that's going to be t times 2 pi little r times dr. And then I want to think in terms of my cylinder. So I'm going to say, well, the volume, I'm sorry, I misspoke completely. Times the density, rather than the linear density. Oh, I said volume density, I'm sorry. I didn't see the density. Yeah, it's the volume density. I thought I just put down volume. I'm sorry. So let's go to purple on this. So the density of this will be the total mass, which is m, over the volume of the cylinder. The volume of the cylinder would be the base area, which is pi times big R squared times the thickness. Yeah, just that front area times the thickness will give me the volume. So then I can do some rearrangements here, and I'm going to say, well, dm is equal to, well, that thickness goes away, and that pi goes away, and so I get 2 big M dr over r squared. So we substitute that into there, and this gives us the integral of r squared times 2m over r squared dr. Let's bring this back here. So I naught is equal to the, let's get our constants out first. Let's get all our constants out first. So we have a 2, we have an m. I forgot my, no, I'm looking down here. I got 2m over r squared. They're all constants. The integral of r squared dr, which equals 2m over r squared, and that's going to be r to the 3 over 3, and that's going to be between 0 and the outside edge, which is big R. That's my sleeve can be near the middle, or my sleeve can be the outer edge as R changes, little r changes. So I is equal to 2m over r squared, and that's going to be r cubed over 3 minus 0 cubed over 3, which equals 2 over 3 m oh, I'm so sorry. I hate to do this, I'm sorry. Back here, I forgot that R. You see that? which means up here I should have had an r, which means here I should have had r cubed, which means here was r to the 4 over 4, which means here it's r to the 4 over 4, and 0 to the 4 over 4, which equals 2 over 4 m times r squared. So I0 is equal to 1/2 m r squared, which equals, which is what my answer is. If you think back to when we did the triangle, the center of mass of the triangle, isn't it the same method? We have a different equation to begin with, but it's again integral, just the same. And we recognize we can't integrate with respect to the thing that we have to integrate with respect to, so we need a conversion factor. And when it was a rod, uniform rod, we used a linear density, and when it was a triangle, we used an area density. And I could have used an area density on this, but now I'm thinking of it more as a cylinder, so I'm going to call it a volume density. And I just work out the conversion factor, shove it in, and then do my integration. I've got to be really careful about not getting little r's and big R's confused. And I'll tell you, if you're not in the habit of doing a diagram, then you're going to pay a price, because you'll get those two backwards very often. And exactly this skill comes up in Physics 2 when we're dealing with charge distributions and the like. So this is not going to go away. So just embrace it. You are going to get a question like this. It's not going to say prove it. It's going to say, figure it out using the method of calculus shown in class. And what I look at when I'm using the method of calculus shown in class, what I look at is, I look and say, is that there? And then I look and say, is that there? And I'm looking for, that. I want to know what you're doing. If you don't do that, at least I want that. I don't want that by itself. I want to know where it comes from. And then I look down here and I go, do you have the right values for your limits? And then you go on. But if you can figure out this conversion and you know the right limits, and you got to do your integration right, but those are the bits I'm looking for. I'm not going to turn around and say you have to do a diagram, but it makes life a lot easier, And just distinguishing between big R and little r is just really important. That's going to be on there. Now, there'll be other times when we don't need, there's three major shapes that I deal with. Let's do that. There's three major shapes I deal with. There's the hollow hoop, where all the mass is around the edge. There's the solid cylinder. And then there's the solid sphere. And this is I is equal to mr squared. I is equal to 1/2 mr squared. And I is equal to 2/5 mr squared. Don't worry about this. I was trying to be clever and make it all divisible by 10, but you won't see it in the books like that. So this is the most sluggish to speed up. And this is the next one to speed up. And this is the easiest to speed up rotationally. I want you to know those. And then not last little bit, but nearly last little bit. Why don't we stop there? Okay? So I'm going to draw a line there. And what I want to do before the end is